Okay, so time is now 10 a.m. in Japan. So let us start today's third JSCE Concrete Committee Webinar, Frontiers of Concrete Technologies. So thank you very much for joining today's webinar. I am Nagai at the University of Tokyo, today's moderator. So to start today's seminar, let me inform you that today's schedule timetable. So today we have a 2 hours seminars. The first 10 minutes, I will introduce about this seminar itself. It is organized by JSCE. And after that, today we have 2 invited researchers. One is Professor Bolander from the UC Davis, and the other is Professor Nakamura from the Nagoya University. We have a 30 minutes presentation from them each, 30 minutes from Professor Bolander. Then after that, presentation from Professor Nakamura. After that, we'll have the almost 30 minutes panel discussion to talk about this topic deeply. So I will moderate, and then if possible, I want to accept some questions from you as well. Okay, to start that, let me introduce the JSCE, Japan Society of Civil Engineers. So this is Japan is one of the biggest academias and engineers society in Japan. They founded in 1914, so that it has more than 100 years histories. And now members over 38,000. Then we have an English homepage as well to expand our technology and knowledge and communicate with you. Then of course, Facebook, and also we are distributing the newsletter. So today you register using your email so that maybe you will have some newsletter as well in the future. And this is a JSCE, Japan Society of Civil Engineers. In that JSCE, we have many research committees. One of them is a concrete committee. We are doing, we belong to this this committee and organizing this seminar. The JSCE Concrete Committee issues the design standard, the standard specification for concrete structures, design, execution, and maintenance as well. And then that a little bit old, but the 2007 version, it's free and downloadable. If you can search on Google and so on, you can get it freely. So if you are interested in, please see and download it. And also we issue the newsletters once, 3 times a year, so that you will receive this newsletter as well. And then we have an international seminar every year before the COVID-19. But in this 2 or 3 years, it's quite difficult to have this kind of international seminar. So then instead, we start this webinar that is Frontiers of Concrete Technologies. So thanks to this kind of IT tech, so we can communicate more, having a wider participants from all over the world. That is maybe a kind of advantage or a good point of this kind of situation. Then actually today is the third JSCE Frontiers of Concrete Technology. We had already 2 times. The first one was held last year, April. Here we invited Professor Ueda and Professor Dai-Jango. And second one, we invited Professor Ipe Maruyama and also Professor Ferreira from Finland. So now you can see these past seminars on YouTube. Actually, we JSCE having our own channel, so that if you search JSCE Frontiers of Concrete Technology, you can see the past seminars as well. Then today is the third Frontiers of Concrete Technology. The title of today's seminar is a simulation of concrete and reinforced concrete structures using discrete analysis model. We invite 2 leading researchers. One is the Professor John E. Bolander from the University of California, Davis, United States. The other is Professor Hikaru Nakamura, Nagoya University. So from now, we will start that presentation from them. But if you have any comments or questions, you can use the Q&A. You can find on your screen the Q&A box. At that time, please fill in your name, affiliation, and comment or questions. But yeah, in the case of last two seminars, it's quite difficult to answer to your all questions, so that I just select a few questions if possible. But I'm so sorry that I cannot answer to pick up all the questions. Thank you very much for your understanding. And also, after this seminar finished in a few days, maybe we will prepare that. Maybe even now, maybe you can watch on YouTube. The live streaming is ongoing, so that not only on this Zoom channel, but yeah, you can see on YouTube as well, this one. But after that, yeah, you can see everything on YouTube, so that you can recommend to your colleagues as well after the seminar. All right, let us move on to the presentations from the invited researchers. First one is from the Professor Bolander for about 30 minutes. So let me introduce Professor John Bolander. He is the professor at the University of California, Davis, United States. Then he received his PhD from the University of Michigan, Ann Arbor in 1989. Then after that, it's quite important for us, for Japan, that he spent about 5 years in Japan at the Kyushu University. At that time, we could have, or Japan could have a very nice experience with Professor Bolander. Then after that, yeah, many Japanese visited the University of California, Davis, and some of them get a PhD from him, and also many researchers, including me, stayed his lab for 1 year or 2 years as well. So that we have a very good communication with him for long years. Then if you are interested in, maybe share. Yeah, I sent to you that some address on chat box. You can see that articles written by Professor Bolander. He kindly wrote the article to JSCE newsletters about his experience with Japan. So that if you are interested in, yeah, please read that article too. Then after he goes back to US, he belongs to the current university, UC Davis. Then he was the editor of the Cement and Concrete Composite. Most of you know that this is one of the top international journal in your field, CCC. He was an editor from 2006 to 2012. Yeah, during that time, the impact factor of that journal is dramatically increasing. It is thanks to him. And then his researches and teaching interest involve the effective high performance material with civil engineers. Then he have been pioneering the development of the discrete analysis model for concrete materials and structures. Actually, that on this topic, Professor Bolander, he is the first researcher who successfully applied the discrete analysis model to the concrete structures. He's really the first. He found this field, so that we are very pleased to invite Professor Bolander today. All right, so I want to ask Professor Bolander to give his presentation for 30 minutes. Okay, Professor Bolander, please start your presentation.
Thank you, Professor Nagai, for the kind introduction. I'd like to thank you, Professor Nagai, Professor Nakamura, all the members and sponsors of the JSCE Concrete Committee for this invitation. I'd like to thank many colleagues, some of whom are in attendance. It's through you that this research was possible and also enjoyable. I'd particularly like to thank Professor Hikosaka for originally inviting me to Japan to work in his laboratory, and for the many fond memories we have of working together. The topic today is quite general, and I'll try to start off with an overview of the subject area, and then narrow down to some of the work that I've been doing with my students and also many of you. So here's an overview of the presentation. An overview this will be about the first half of the talk, and quite a bit about modeling reinforcement, short fibers in particular. And then finally, just one simulation example, and that's for plastic settlement of concrete at early age. So we are interested in not only stress analysis, but quite often we're interested in other field variables, including temperature and humidity. These together affect the performance of the structure over its life cycle. So one of our goals, along with testing and field monitoring, is to try to simulate these cases. And traditionally, many of you know that finite elements have been used for this purpose. And the topic of today's discussion is discrete methods. So one of the main differences between these is for finite elements, each element is composed of at least 4 nodes in 3 dimensions. And for discrete models, each element is simply 2 nodes. So for the continuum methods, we have a description of all the field variables, be it temperature, humidity, displacement. We have a spatial description of all the field variables within each element, within the whole domain. And for this discrete methods, we only have a description along the line between the 2 end nodes of the element. So that's one big difference between continuum approaches and discrete approaches. Within the discrete approaches, we can subclassify them into different approaches. I was initially inspired by the work of Jan van Meer and Eric Schlangen, and they were working with so-called classical lattice models. And then later on, through Professor Hikosaka and Dr. Liu in his laboratory, we started working on rigid body spring models. And we can classify RBSM as a particle-based lattice model. I think it's very important, those of you that are developing rigid body spring models, to see this linkage to the classical approaches, such as lattice models and the discrete element method. We recently wrote a review paper on these discrete methods, particularly with respect to modeling concrete fracture. So the classical lattice models, now I'm just doing some review. We, first of all, need a description of the material structure. And then we superimpose that on a lattice. And these lattice could be ordinary truss elements or frame elements. And here, throughout the analysis, the element connectivity or the nodal connectivity remains constant. And we model heterogeneity by what I just said, mapping an image of material structure onto the lattice. And originally, fracture was modeled as simply removing the element. Elements that violated a fracture criteria were removed from the network. And so this is what I was initially inspired by, the work of Jan van Meer and Eric Schlangen. particle-based lattice models are slightly different in that each node is associated with a particle. And we often use the Voronoi diagram to define the boundaries of these particles. And so we still have, each element is still composed of two nodes. The nodal connectivity remains constant over the course of the analysis. Any two particles form an element. And then here's something I'll try to talk about today, and that's that this discretization has either physical or non-physical meaning. And I'll come back to this thought again and again throughout the talk. The discretization has either physical or non-physical meaning. Here's one example. This element that spans the interface between, let's say, an aggregate particle and the surrounding matrix has physical meaning because the element itself is representing the interface. The element is perpendicular to the interface, and we can control the thickness of the interface. And since the element is perpendicular to the interface, it's much easier to control the properties when it's fracturing. In most cases, this element is non-physical. It's just purely there for discretization. We could think of these as being particles of real material, but then things become a bit complicated. So in my view, this is a form of non-physical discretization. It's just there to discretize the domain, and it doesn't relate to actual material features. So we begin with image data. The image data could be physically mapped, say it's coming from computed tomography, or we synthetically generate it. Originally, most of the synthetically generated aggregate structures were circular disks or spheres. If you go to the literature now, there's much richer ways to simulate aggregate shapes. It's really amazing what can be done now. So that the aggregates no longer have to be spheres. They can be quite realistic in shape. So once you have an image data, you map it onto a lattice. At the very fine scale, we can discretize each aggregate and its interface in this way. You notice that there's many elements perpendicular to the interface. So we're explicitly discretizing the interface, and we can control the thickness of the interface as well. Next up, the ladder. And there's my pointer. We just project the lattice onto the image or the image onto the lattice, and we're still representing interface, but there's no longer that direct representation. The elements are not necessarily perpendicular to the interface. These are very expensive, and we can't imagine discretizing large volumes of concrete in this way. So let's take it one step coarser and say that there's a node at the center of each aggregate, centroid or some other place within each aggregate, so that one element represents two aggregate particles and the matrix material that lies between the two particles. Going one step coarser, we have a discretization that semi-relates to the underlying material structure, but there's no explicit representation of material structure. Rather, the element size and the random geometry reflect heterogeneity. And then finally, up here, there's no representation of material structure. It's just a pure discretization strategy. I just point out this is one of the state-of-the-art accomplishments, and that's the work of Kusadas and his group at Northwestern University. He's working at this level. So for him and his colleagues, Each aggregate particle is there's a node in each aggregate particle. And they're able to produce these types of cracking patterns, which is quite remarkable considering the scale at which they're discretizing the material. As you know, many of you know, I've been using rigid body spring models that were introduced by Kawai many years ago. And for us, we're using a Voronoi diagram. And you're seeing here a discretization of a cube. These are Voronoi cells. And then the connectivity between the cells are the Delaunay edges. So this IJ is one element within the volume. I like to represent the elements this way. Instead of showing two particles next to each other, I like to view the element in this way, because this is all that matters. The two nodes, the Voronoi facet that's common to the two nodes, and their connection at the centroid of the Voronoi facet using a zero-size spring set. So we have, for 3D problems, we have 3 springs. One is normal to the facet, then there's 2 tangential to the facet. And they're connected, the spring set is connected to the degrees of freedom at the two nodes and nodes through these rigid arm constraints. That's Professor Kawai's idea. We can generalize this instead of just using springs, elastic springs. You see here's an elastic spring. We can include hygral or thermal units for multi-field analysis. And we can also account for concrete creep, both viscoelastic and viscous components. And these can be driven through models of cement hydration so that we can model property development over time. So over time, we model cement hydration, and then the spring properties change as time goes on. To model fracture, this is one simple way to model fracture. We have the force in the normal spring, the force in the tangential spring, and we'll take the resultant force of that, and we'll say that's the principal direction. And then according to that, we'll let cracks form perpendicular to the principal tension direction. And what's neat about this is that the volume of the crack band, this is the crack band concept of Bajant and O, is defined by the Voronoi diagram. So the bounds this way are the nodal points. The bounds this way are the tips of the common Voronoi facet. So in this way, we can compute stress and then soften the material according to a prescribed softening diagram. And in doing this, we can nicely model softening for the uniaxial tension case. Much of my work has dealt with uniaxial tension or mildly mixed mode situations. It's much more complicated when you have compression and other stress conditions. So here's another demonstration. This is a split cylinder simulation. It's a 3D simulation. And there's a circular aggregate in the center of the split cylinder test. And we see debonding initiating just to the side of the cylinder. And as we increase the diametric compressive load, the cracks emanate from the center and propagate towards the load platens. This is a 3D simulation, and notice how nicely localized the crack is. We don't have any artificial peripheral damage to the sides of the crack. In many cases, we're interested in the stress tensor at the nodes of our model. And for many years, we had a complicated procedure to calculate the stress tensor. And then one of my colleagues, Gunhui Kim, who was at Lawrence Berkeley Laboratory, pointed me to this simple formula. And so now we're using this. And so we can calculate a tensorial measure of stress at the nodes placed within the Voronoi polygons or polyhedra through this simple relationship. So these T1 is the force of the spring set in the X direction. T2 is the force of the spring set in the Y direction. And X is the spatial coordinates of this facet centroid with respect to the node. And through this formula, we can calculate tensorial measures of stress. And then we can compare with theory. And a sticky point, which I'll come back to a couple times, is Poisson's ratio. Long ago in our early research, we assumed that Poisson's ratio was 0, and we could get very nice results for that. But for non-zero Poisson ratio, we had trouble until the work of Dr. Asahina. And so through his work, and these are 2 publications that he led on, we're now able to model Poisson's ratio for the complete thermodynamically admissible range from negative values all the way up to 0.5 without any trouble. Conventional approaches, which I'll come back to in a moment, produce this sort of noise, meaning you're getting approximately proper stress values, but there's a lot of variation from theory. So here's another demonstration. A key point is we use the normal spring stiffness and the tangential spring stiffness are equal. That's the basis for Asahina's formulation. That's our starting point. And then we have an iterative algorithm to introduce Poisson's ratio. In the conventional approach, Poisson's ratio is simulated by making the normal and tangential springs non-equal. And so we're able to simulate Poisson's ratio in a macroscopic sense, but locally there is some variation. So for example, originally Kawai proposed the normal spring and the tangential spring would follow these relationships depending on Poisson's ratio, Young's modulus, the area, the common facet between the nodes, and the distance between the nodes. So let's look at what happens when we subject this panel to pure shear. For pure shear, the horizontal displacement should equal the y coordinate or some fraction of the y coordinate. And the vertical displacement should equal the horizontal coordinate or some fraction of it. And when we do this, the displacements from the conventional approach have a L2 error norm on the order of 10 to the minus 3 or even 10 to the minus 2. Using this elastically homogeneous approach, there is no error. It matches theory to within machine precision. These numbers might be hard to interpret, so let's look at a picture. This is the type of noise from the conventional approach that you reproduce. This is normalizing major principal stress by the theoretical principal stress. So we hope to see 1 everywhere. We hope to see a value of 1, and yet we see this scatter. What's interesting is there's actually a directionality to the scatter, and this is something we're investigating, that for different loading patterns, you don't see a completely random distribution of nodal stress values, but there's some directionality to this, which is interesting. Here's another sample problem. It's a bimaterial, it's a inclusion, and let's say the inclusion is stiff, and it's surrounded by a compliant matrix. The boundary condition is we're just subjecting this outer perimeter to a uniform radial displacement. And when we do so, the approach that Dr. Asahina did, so Poisson's ratio is obviously important here, almost matches theory. This is for the case where there's a stiff inclusion, it's 10 times stiffer than the surrounding matrix. This is the case where it's just a homogeneous material. So either way, we follow the exact solution fairly closely. Using the conventional approach where the normal spring stiffness and the tangential one are not equal, there's a reasonably good fit for this uniform case. When I first saw that, I said, wow, there's no noise here. Well, it's because under this radial displacement, you're not activating the shear springs. Only the normal springs are activated. So you don't see any noise here. But when you stiffen the internal inclusion, there's a stress gradient. And so now you activate the shear springs and you see quite a bit of noise local to that interface. So many of the applications, if not all, involve some sort of reinforcement, either steel bars or short fiber additions. We've modeled short fibers by starting with the same rigid body spring network, following the ideas of Professor Kawai, and then randomly placing fibers within the domain, and wherever a fiber crosses a Voronoi facet, we introduce a fiber element. And it follows the same ideas for the 3D volume of material, but now there's just one spring, and the spring is aligned with the direction of the fiber. And because our matrix is elastically homogeneous, we can, this is before cracking, we can simulate the stiffening effects of the fiber over its interior and the shear lag effect at the ends of the fibers. So if I went back a couple slides and we look at this type of noise, if you put a fiber in here, you won't see the fiber so clearly as this. We don't get this nice result when there's that noise present. The effect of each individual fiber is harder to simulate. So when the material fractures, we can introduce a micromechanical model that relates bond slip and bond stress. Then the fiber bridges the crack, and these two together produce this type of bridging force as the crack opens up. So we can have a material that slip softens or slip hardens. You get this type of response for slip softening and slip hardening respectively. Then finally, when you look at the multitude of fibers in collection, depending on the properties of the fibers, the amount of fibers, their directionality, you either get one crack with pullout or you get multiple cracking. Multiple cracking is shown here. So we simulated this type of case. Again, you can just throw the fibers in, irrespective of the background mesh, the geometry of the background mesh. And with these discrete methods, you simulate displacement continuities naturally such that you can get these closely spaced cracks. This is difficult to do with continuum approaches. The cracks, each crack is nicely formed and you don't see damage between the cracks. So the cracks localize nicely. And that's an outcome of using two-node elements, I believe. So that's a good feature of discrete models. Here's an animation of this process. And so this is just in pure tension, and this is strain hardening, and then you see localization, which leads to failure. And so we can simulate not only the multiple cracking and the localization process, but the peak strains match experiment fairly well, and the peak loads match experiment very well. And what we were really interested in was the histograms of crack opening. This is important when estimating the durability of some protective schemes or some application areas. You're interested in how wide are the cracks. And so for low strain levels, we match experimentally observed crack opening histograms fairly well. And then you get to some point where the two diverge. And that's because we're using a coarse mesh, and the mesh becomes saturated. You need a finer mesh to keep up with the experiment. So this is for mechanical behavior of reinforcing components. Some of our recent research, we've been looking at how reinforcing components act to modify transport processes. And we'll begin by treating each fiber as a volumetric entity. So each fiber is modeled as a volume. And if the fibers have the same material as the background mesh, you can run potential flow through the model and there's no bias produced by the mesh. If the fibers have different properties, then and this is more realistic, you can see how the fibers modify the flow field. And so again, each fiber this is a fiber cross section, and it's very expensive. You can imagine how many nodes you need to model one fiber. So this is expensive, but in some ways accurate. We were interested in the composite properties, so we had to introduce periodic boundary conditions. So a fiber exiting one boundary comes in the other boundary. If you don't do this, the boundary effects mess up the analysis. So we need these periodic boundary conditions. And so all the ones that are yellow in this figure, the fibers that are yellow are ones that have intersected a boundary. And the blue ones are the ones that reside completely within the volume. Alternatively, and this is recent work, we can go back to that concept that I showed you a moment ago when we were modeling the mechanical properties of fibers and introduce conductivity enhancement wherever the fiber crosses a Voronoi facet. So the fiber, you just sprinkle the fibers in, put the fibers at anywhere within the model, and just wherever the fiber crosses a Voronoi facet, we modify the properties of this transport element to account for the presence of the fiber. And a key point here is in your conductivity relationships, we don't use the entire length of this element. We don't use the entire length of IJ, we use the projected length for the properties. And in doing so, we can model the effects of the fiber on the flow field nicely. So in the top half of this flow contour, we're using an approach where we discretize the volume, the fiber as a volume element. And in the bottom part, we're discretizing as without volume. It's just line element approach. So now we can sprinkle the fibers in anywhere and see their effect on the flow field. And so coming all the way back to this case, now we'll do the composite simulations here, and we're comparing with theory. You have upper and lower bounds according to Hashin's Strickland solution. And more accurately, we're comparing with the work of Hata and Taya, who used Eshelby's equivalent inclusion method for elasticity problems, and then mapped it over to the potential flow calculations. So this is the theory that we're comparing with. So they have the amount of fibers, the conductivity of the fiber, the conductivity of the matrix, and the dimensions of the fibers. In the theoretical derivation, the fibers are really long ellipsoids. That's how they're modeled. And we can see when we use the volumetric approach, where we discretize the whole fiber volume, we almost match the theory. The scatter that you see here is because we're doing different random realizations of the fiber distribution. In some cases, the fibers are pointing in the direction of the flow just by chance. In other cases, they're more perpendicular to the flow. And so this is, how many were there? Like 7 random realizations produced this scatter. Using the semi-discrete approach, we get almost the same results, although there's some drift of the solution upward. Our line element approach is slightly more conductive than theory. And I think I understand why. And so lastly in this talk, we'll bring some of these tools together to simulate plastic settlement. This is interesting because it's a coupling between high growth phenomena and mechanical phenomena. So it starts with a volume of fresh concrete. Say it's in this box. We have a volume of fresh concrete, and at early age, the material is not quite a solid. It's more like a fluid, and the cement particles have higher specific gravity. They tend to settle, and the water within the mixture transports up to the free surface. And so this can be modeled in different ways. We're modeling this phenomena based on Biot's effective stress concept, as described in these 2 publications. And so we're able to, this is no fibers yet, the concrete by itself will settle over time. And so the rate of settlement is high in the beginning, and then as time goes on, the rate of settlement decreases until you reach some plateau. And so whether our lattice is 1-dimensional, 2-dimensional, 3-dimensional, it compares nicely with finite element results. So now we add the fibers, and there's some assumptions we have to make. That cement hydration is not occurring over the time period of interest. The fibers are elastically bonded. That's a big assumption. Think of the material at that early age. We're assuming it to be elastically bonded to the matrix material. The fiber matrix interface has enhanced porosity. This is reasonable, particularly for hydrophobic fibers like polypropylene fibers. The transport along the fiber matrix interface is modified by modifying the conductivity of the fiber, and the fibers are isolated from one another. In doing so, now we can simulate the effects of fiber additions. So for no fibers, we see a curve similar to what you saw 2 slides ago, that at early age, there's well, this is at 1 age, pardon me. At 1 age, at a certain depth, at a low depth, you have little settlement. Up near the surface, you have the greatest amount of settlement. And there's no scatter in these values because our model is elastically homogeneous. Then as you add fibers, 2 things happen. 1, you reduce the amount of settlement. The fibers stiffen the mixture. And 2, you see some scatter in the nodal values. And that's because of the random distribution of the fibers within the material. So this is a stiffening effect. The fibers stiffen the material so to reduce settlement. Conversely, when you add fibers that conduct water flow, you relieve the pore pressure distribution near the bottom of the concrete. The water can move upward more freely, which accelerates the settlement. So you have these two different competing effects, stiffening effect and enhanced conductivity, which increases the settlement. And when we plot the two together, you can see that here, as I add fibers, I'm going down. This is 2% fibers. This is 0 fibers. There's a stiffening effect of fiber addition. Here, as I add fibers, I'm increasing the settlement. If I look at each case in isolation, when the two are combined, we see that adding fibers increases settlement at early age, but ultimately decreases the ultimate settlement. And this is good because we want this enhanced conductivity at early age because it brings water up to the drying surface. So we don't get as much surface cracking. And also we don't have a large plastic settlement at later age. One of the next steps we'd like to do is model cracking. So here's where I'd like to collaborate with you. How does this crack at age of 2 hours, age of 3 hours, age of 4 hours? This is an area of research that I think is quite open. These materials are under sustained loading. These settlement and shrinkage and so forth, it's a sustained load. The material is very young. How do we model cracking at these early ages? It's a real challenge. And so to summarize, the choice of modeling framework, we have two basic choices. We can go with a continuum model or a discrete model. I think it's hands down that discrete approaches handle crack formation more simply and more naturally. The element formulations are simpler. The two-node elements allow you to model separation processes without locking. So this is one of the main reasons to use discrete approaches is for modeling cracking. However, stress strain analysis are complicated by the Poisson effect. And I showed you several examples that because of Poisson's ratio, we can get noise in the stress and strain fields. And this can be something that we use to our advantage, or it could be a disadvantage. If you're just modeling scalar fields, by that I mean temperature, humidity, there's really not much difference between using finite elements or discrete models. When you discretize the structure, you have a choice of making the discretization something physical or non-physical. If it's a non-physical discretization, the mesh geometry, the mesh size should not bias the solution. And this is where I've tried to work. And most of my work is with these non-physical discretizations. It depends on the goals of the analysis. When we model reinforcing components, including short fibers, we have a choice between modeling the volume, the full volume of the fiber, or modeling the fiber as a line element. And there's advantages and disadvantages to each. The volumetric approach is expensive, but more accurate. The line element approach is computationally much better in terms of cost. We can put these elements freely within the domain. We can model the pre and post cracking influences on composite behavior. And as you've seen through the example I showed, we can use them for multi-field, multi-scale analysis. regarding this hygromechanical simulation of plastic settlement, the fibers mechanically serve to reduce the plastic settlement. However, the fibers might have porous interfaces, which can increase the bleeding rate and therefore the plastic settlement. So you have these two competing effects. When you combine them, however, you get an initial increase in settlement, but the overall settlement amount is reduced, which is good. I think this is just one of many areas where we could collaborate. We're interested in modeling cracking at those early ages. And all of that work has to be validated through comparisons with physical test results. Thank you for your attention.
Okay, thank you very much, Professor Bolander, for your nice presentation talks, and especially the very basic fundamental theory of the RBSM and the relationship with other models and the meaning of the scaling and so on. And also, yeah, I'm really interested in the meaning of this method, yeah, compared to the FEM continuous method. Mm-hmm. And even this is a discrete model, but you try to keep that homogeneous some material property before the cracking. So that some of us, including me, often ignore some parts or don't try to see that or something. So that, yeah, they are really good topic to discuss, maybe with Professor Nakamura. So because Professor Nakamura will present rather on the application side for the concrete structure, so that maybe we better have a presentation from Professor Nakamura. Then in the panel discussion part, I want to ask you about more on this topic. Is it okay?
That sounds good.
Yeah. Okay. So let us, yeah, time is also a little bit behind, so that let us move on to the next presentation first from the Professor Nakamura. Can I get the screen? Okay, thank you very much. Okay. Okay, yeah, Professor Nakamura. Okay, yeah, thank you very much for preparing the PowerPoint, but just let me introduce him shortly.
Okay.
Yeah, just please
I stopped the sharing.
Sorry sorry that. Yeah, I can you see that?
Mm-hmm. Yes.
Okay. So yeah, let me introduce Professor Nakamura again. Yeah, many of you know him, but he's a professor at Nagoya University now, and he got the PhD from Nagoya University in 1992, and his research interest is in the numerical analysis and also rather structural side, seismic design or maintenance or NDT for concrete structures. So yeah, he's rather on the structure side, so that he was doing the really nice research on the shear failure of the reinforced concrete. And so he used FEM as well, so that he knows very well about computation and also the structures. Then he's now a director of the JSCE, Japan Concrete Institute, and so on. And also he's also a member of the editor of the CCC, and also the Advanced Concrete Technology. This is an international journal from Japan. Anyway, that we'll have a presentation from Professor Nakamura on the application of rigid body spring method and its impact to the structural research. Okay, yeah, Professor Nakamura, if you are ready, yeah, please start your presentation. I will use the screen.
Okay, thank you for kind introduction. Yes, I prepare the slide.
Okay, now we can see.
Can you see the slide? Okay,
yes,
so,
please.
Okay, I'd like to start my presentation. Firstly, I thanks to Professor Nagai and your colleagues and Professor Bolander to give a chance to talk together about the discrete analysis model. And Professor Nagai introduced Professor Bolander. Professor Bolander is just a pioneer. My research start from to read your papers, and now I'm working at Nagoya University. But before I worked at the Yamanashi University. Then one of the Professor Hikosaka and Professor Bolander student, now he is Saito, now he is a professor of the Yamanashi University. I worked him together and I learned the many information about the Bolander, Professor Bolander's achievement. So my all topic is based on the Professor Bolander's research, and he present very basic and fundamental aspect of the discrete analysis model and rigid body spring method. And I apply based on his knowledge and development the several problems of the concrete structures. So today I'm going to talk about the application of rigid body spring method and its impact to structural research. So this is today's content. First, I'm going to explain about the motivations, the reasons to use discrete element model. And next, I show the several application results of RBSM. Mainly my interest is the structure side, applied to the structure side and member levels. So I explain the several application results to the member levels. And finally, I'd like to discuss about the impact to structural research by using the discrete element analysis model. So, first, I would like to talk about the finite element method. In past 3 decades, nonlinear analysis, especially finite element method for concrete structures, has advanced remarkably. Of course, it was achieved to combine the constitutive model, numerical algorithms, and analytical theories and modeling. But there are some problems. This shows the simulation result of RCP failed in flexion. The load displacement relationship can be simulated reasonably. However, compressive strain localized an element, and the damage zone is quite different with the test result. This is a famous localized problem of softening material of finite element method. So, finite element method can easily solve the global behavior, such as the load displacement relationship. But sometimes it is difficult to solve local behavior. On the other hand, according to the development of numerical method, our requirement should be moved to simulate accurately local behavior such as cracking and compressive failure. So, do you agree with this requirement? So, my motivation, why do I use discrete analysis model is that first is that the model can directly and easily simulate the cracking behavior. So Professor Bolander concludes that the merit is the cracking. That can show the naturally and reasonably, realistically. A discrete model have advantage to reproduce individual crack behavior more than general smeared crack continuum model. And crack affect not only the safety, but also durability. Therefore, good durability assessment method require realistic cracking behavior, such as crack width and crack propagation. Second, motivation is for failure stage. Not only maximum load, but also post-peak behavior. We have learned the importance to understand the failure stage from several accidents, such as a big earthquake. Safety design can be achieved by accurate understanding failure process. We need to reproduce the realistic localization fracture behavior, such as damage level and damage zone as discrete phenomena. So based on this motivations, I applied the several problems. So going to show the result. First is applied to the members level subject to the external load. But the first, I also introduced about the RBSM. And RBSM is analytical model to simulate structural behavior by springs and between the rigid body. And now the advantage is that the combined with the vulnerable particles. That is a big jump to apply and extend the application of the RBSM to concrete structures. And then in our model, a number of springs are set in boundary of each surface. The setting of springs is different by researchers. So Professor Bolander mentioned that the case is a spring set the 3 direction at point. And the feature of our model is that several integration points are set in an element surface. And one integral point has 2 kinds of the spring, normal and shear spring. So the advantage of this model is that this model can evaluate the effect of bending and rotational moment automatically in the surface without rotational springs. And I'd like to note that element size is usually assumed about 10 to 30 millimeter, as same as aggregate size. These are concrete material model. This is a tensile and compression model of normal springs. The feature of our model is that no softening part is modeled in compression. The stress increase, like under the hydrostatic condition. The concept is important. Compression failure is not compression failure of concrete. It is accumulation of failure of tensile and shear failure. If we model crack directly in aggregate size, compression failure model is not required. Material model depends on modeling scale. This is a model of reinforcement. Reinforcement is modeled by beam element and is attached to the concrete particle through zero-size link element. Moreover, bond property is introduced into the shear spring of linked element. The bond is important to control crack. I will show several results to simulate mechanical behaviors. This figure shows the simulation result of uniaxial compression test having a diameter of 100 millimeter and 2 different height of 200 and 400 millimeter. The stress-strain relationship agree significantly well with the test for different size. And this shows the strain distribution along the height, test and analysis, and the deformation from pre-peak to post-peak obtained from the analysis. The reasonable simulation of localized area and actual local strain distribution and its development can be seen. Next is example of bond behavior simulation of this test result. It is well known that bond strength increase of cover thickness. This case is changed to 10 to 50 millimeter. And sometimes many parameters such as cover thickness are modeled in constitutive model in finite FEM. And this is a numerical model of RBSM. Deformed rebar is modeled by beam element, and a simple local bond strip model is assumed. Only the function of compressive strength. We did not consider more parameters such as the effect of the cover thickness. Through the simulation result, please confirm what is the difference between FEM and RBSM. This shows the comparison between test and simulation result of different cover thickness. In order to understand effectiveness of beam model of rebar, I make another model by using the 3D rebar model with lag. So the result of 3D rebar model with lag are also shown together. So black is the beam model and dashed line is the 3D model. It is confirmed that beam model with local bond model and Voronoi mesh can simulate bond strip behavior with different cover thickness like 3D rebar model. And important point is that internal cracking pattern is also simulated like 3D rebar model. Of course, 3D rebar model models the lip, so they can simulate the stress transfer from the lip and reproduce the inclined crack from the lip part. But the beam model success to simulate similar with 3D model. Why can this simple model simulate not only bond strip but also internal cracking behavior similar with 3D rebar model with lag? I simulate by regular mesh arrangement. Then the model, this is the model. The model could not reproduce the effect of the cover thickness and internal crack pattern. They show the same result even in for the different cover thickness. Key aspect is random mesh modeling. I modeled only bond stress along the rebar, but the stress is transmitted to arbitrary direction by random shape. This random shape worked as similar with lag and tip of deformed rebar. So combination of Voronoi element and beam element gave us new possibility of RBSM to simulate many problems related to the bond. This shows the result of cyclic shear wall tests. The tests were conducted by National French project. It's not new, 10 years ago. And this is a crack pattern obtained from RBSM. White dotted line is the test result. Colored line is the result of the RBSM. RBSM succeed to simulate crack pattern such as the crack angle and crack space in blind. I think that it is difficult to simulate detailed crack pattern by FEM. This shows the several results of RBSM for member simulation. This is a shear failure simulation of RCP. The analysis was performed before test. Professor Bolander shows the result of the cast to simulate the shear behavior. So our cases are also can simulate the realistically the shear behavior. Not only the load displacement relationship for different shear startup ratio, but also the crack pattern. Black is a tested crack pattern and color is a simulated crack pattern. This is correction failure of PC file. It shows similar failure zone and failure behavior. And this is the dynamic behavior of RC building, very big scale structures. Next is now that I explain about only the problem subject to external load. Next is to consider the several physics problems. I show the result of structure analysis subject to external load, but the time-dependent analysis is more important to evaluate deterioration of structure performance. Then, most deterioration behavior are related to mass transport, such as the thermal, water, chloride ion, so on. Therefore, for time-dependent analysis, combination between structure analysis and mass transport analysis is required. I combined mass transport analysis with RBSA. Then, truss networks model is used for transport analysis considering the consistency with the concept of RBSM. Since RBSM is composed by link of truss element. The merit is that one-dimensional diffusion equation is employed to carry out mass transport. It is a very simple. And the mass transport through crack is more important because after cracking, the mass move through crack rather than within bulk concrete. Therefore, the mass transport through crack is considered by generating the truss on particle boundaries, which is the crack plane in structural analysis. Then, different conductivity in bulk concrete is assumed, and the cross-sectional area is decided by the crack width calculated by RBSM. The modeling was achieved by using the advantage of RBSM to be obtained crack width directly. So that this idea is I forgot the detailed years, but 2003 or 2003, the Professor Bolander had the lecture at the Nagoya Institute of the Technology. Professor Ichinose invited him, and he had the lecture. He explained the transportation problem, applied the transportation problem in the RBSM. Then I get the so how to consider the crack plane and get a new idea to consider the combination with the crack with that mass transportation. So thank you for your very nice lectures. This table shows several mass transport problems such as molecular diffusion, temperature, water, and electric. Primary equation is same. Therefore, every mass transfer can solve same way using simple truss element networks. This is a several application of coupled method. This is a loading analysis concerning drying shrinkage with moisture transfer and river corrosion with chloride ion penetration. And the cover spalling is observed due to the corrosion crack along river. So the corrosion crack along river occurred by considering the chloride ion corrosion process and apply the load due to the arch action, the spalling behavior occur. This is a shrinkage crack analysis concerning drying shrinkage with moisture transport and creep. So we can observe the drying from crack. This is fire spalling analysis concerning heat and vapor pressure transport. I pick up an example to explain slightly detail. This is a simulation of radius loss and crack propagation due to river corrosion. In the simulation, electromechanical model was combined with rigid body spin model to simulate cracking behavior, truss network model to simulate electric potential, and local corrosion model to consider expansion pressure. We consider that during the electric corrosion test, the corrosion is mainly controlled by the applied electric field. So truss network model deal with flow of electricity. Hence, first we use Laplace equation to calculate the potential distribution. Secondly, based on this result, calculate the current flow by Ohm's law and the mass loss by Faraday's law. In this way, we can calculate the radius loss around the river depends on the time, considering the distribution of the potential. From the radius loss, the distributed expansion pressure can be automatically determined. The expansion pressure is applied by an initial strain problem. And in order to consider the electromechanical coupling with crack, the effect of crack is considered by changing current efficiency with crack. To be used, the function of crack width is the advantage of RBSM. The feature of the method is that all results can simulate automatically in time. Time is only control factors. This is a simulated result of uniform corrosion along river. This figure shows the simulated corrosion degree against the current flow. We can see when crack effect is considered, the simulated corrosion process is similar to the test result. That is, the corrosion degree increase after cracking in proportion to the current flow. This is the predicted residual cross sections. They are similar to those measured in the test. Marked line is the test result, and solid line is the simulated result. And moreover, the simulation also demonstrates that the generated crack can enlarge the difference of the corrosion rate between the top and down sides. This figure shows the simulated internal crack pattern at the same time with test result. We can see the simulated crack pattern agree well with the test result at the same time, not only in the pattern, but also in the crack width and length. So I showed the several applications of the RBSM, and mainly our interest is discrete analysis crack, and discrete analysis method can simulate cracking behavior accurately. So what can we see through crack? We have observed many damaged structures due to big earthquake. What a lesson from damage due to big earthquake? We have to understand ultimate behavior more. It is not only design stage, but also the collapse stage. Then we have to consider the crack separation and crack accumulation behavior as a discrete manner. And we have to prepare other excessive action, such as the collision and fires. Then we have to understand and to model dynamic crack propagation. What can we see through another crack? We have observed many damaged structures due to deterioration. What are lessons from collapse of bridge and tunnels? The importance of maintenance is increasing. So we have to evaluate deterioration of structure performance with time. Then actual crack modeling and evaluation are key issues. And I showed the several numerical results. What can we see through simulated crack? What are lessons from advancement of simulation method? We should discuss more about what is the merit of discrete analysis model than finite element method, how to verify accuracy and reasonableness of simulation result, how to use many information obtained from simulation results. What do we get from simulation result? What are impact to structural research field? So as a final part, I would like to discuss impact to structural research from the consideration of the numerical side. This shows the simulation result of test shear failure beam by RBSM and FEM. Load displacement relationship before shear capacity are similar with test result, both RBSM and FEM. But the crack or strain distribution at the side surface or in cross-section are quite different. Usually, only the load displacement is compared with test result to verify the accuracy of numerical result. Is this situation appropriate? The discussion of requirement or utilization to analysis is important to advancement of simulation method. We have to discuss advancement of experiment as well as numerical simulation. Information from experiment should be same level with simulation. So we have to get information not only load displacement, crack pattern, strain at some point, but also distributed information outside and inside specimen. In order to achieve the motivation, currently the latest measurement method, such as optical motion capture system or digital image correlation method, is often applied in experiment. This is an example that the method was applied to the simulated shear failure beam at previous sheet. This shows result of optical motion capture and DIC. This figure shows the incremental in-plane displacement is indicated by arrow and incremental out-of-plane displacement is indicated by different color. And this is the result of DIC indicated by different color. We can understand that how deform all position in space three-dimensionally and how propagate or open the crack even for small crack at all loading stage, not only the peak, not only the after the test, and in the all loading stage, we can get the many information. Therefore, the simulation result should be verified by comparison with many information. The information was the observation from outside, but the internal information is also important and has worth to utilize with numerical result. This is one example about the procedure to get internal crack pattern. This is an example of observation of crack at a section. By performing the process to all sections, 3D internal crack map is described like this. I think the 3D internal crack map is probably the first trial in the field of RC structure. This shows the crack pattern in cross-section obtained analysis and test at different sections. The interesting finding is that horizontal crack at mid-height in the area and inclined crack propagating to corner were observed. RBSM is also simulate the behavior. When we use 3D modeling in the analysis, are we using the 3D information? When we use the 3D model, we have to show the 3D information, and we have to compare the 3D information obtained from the test. Based on the detailed discussion of tests and numerical result, what do we get from simulation result? This shows just simulation result of shear failure beam that only the vertical leg space changes to keeping the startup ratio. Design shear capacity are same for same startup ratio. But the simulated load displacement relationship are quite different. How do you think? Why is this difference occur? We observe the difference from internal crack in cross-section. For large leg space case, which is a usual closed startup, it was observed that crack initiate at the center, shear crack initiate at the center, and propagate horizontally after diagonal shear crack occur. That's point. But crack propagate diagonally to corner near peak load, and cross-section expanded in the width direction. On the other hand, for small leg space case, cracks propagate horizontally in the cross-section, but could not propagate diagonally in small space. I think that is the reason that due to the small space, crack cannot change the propagation direction. As a result, cross-section do not expand in width direction. Probably the difference of crack propagation and deformation in cross-section influence to shear capacity. This is just the simulation result, but do you agree with the discussion? Important point is that detailed observation of numerical result of advanced discrete analysis will give us the possibility to get new knowledge to structural research field. So this is the final sheet, and what can we see through discrete analysis method? Discrete analysis method can simulate realistic behavior of concrete structures based on fundamental mechanical behavior related to minor and major crack initiation and propagation, naturally and realistically. And both the advancement of numerical and experimental technique are important. Numerical and experimental technique should be advanced together. Especially, numerical side should require to experiment the side based on the knowledge obtained from many information. So this is I show the several my papers, but the many result is related to the RBSM I published from the Journal of Advanced Concrete Technology. This is the structure analysis. This is the durability and corrosion part. So that if you need more information, please come to the homepage of the Advanced Concrete Technology and check my papers. Thank you for your kind attention.
Sorry. Okay, thank you. Sorry for that. Yeah, thank you very much, Professor Nakamura, for your impressive presentation, including the various applications to the concrete structures that includes the dynamic phenomena, and the shrinkage or corrosion or chemical phenomena, and also using the CANDU or transnetwork, the substance movement as well. So that maybe most of you, the participants, can feel the possibility of the discrete analysis model for the design and maintenance of the reinforced concrete structures. So yeah, from now we want to move on to the panel discussion part. So, but yeah, Professor Nakamura answered already to my question I prepared, so that yeah, for example, yeah, compared to FEM, what advantage or experimental simulation or V and V as well. Okay, so firstly, let me go back to the presentation by Professor Bolander. So maybe that you can see that questions from Professor Kunieda. Maybe I will show that. Okay, so second one, I'm sorry, I haven't yet confirmed, but maybe this question would be good to Professor Bolander about the simulation itself. When the simulation keeps the good homogeneity or theoretically correct, but in reality, or if you publish the journal paper, always you need to have a good result with experiment and so on. So that the meaning of the modeling or keeping that theoretically correct equation modeling, what can we do? Or is there any opinion about this kind of gap? That would be included to your presentation. You show the importance of keeping the homogeneity even this is discrete crack. So can you give some comments on it, Professor Bolander?
Thank you for the question. Thank you, Kunieda Sensei. We agree that it's important to model the heterogeneity. So our philosophy is that the background model should be elastically homogeneous. And then we introduce the heterogeneity through, for example, a spatially correlated random field. Or is the example that was given in the talk, when we add fibers, the fibers are a form of heterogeneity. So we can introduce the heterogeneity in a controlled manner, rather than having it as an artificial outcome of the background lattice. So it's, and this is just our viewpoint, is that we have a little bit more control over heterogeneity. So that's in short, that's we agree with the question. we must model the heterogeneity, and so our trend is towards controlling that heterogeneity through, say, a spatially correlated random field.
Okay. Yeah. So the comment from me, or the additional question, is that you show that some random field when we just use some just basic RBSM model. I mean, you show the slide that shows some non-homogeneous stress field. But we sometimes when we apply this kind of method to the concrete modeling or concrete problems, the concrete is always homogeneous, heterogeneous material. So that somehow we can ignore this kind of stress distribution or randomness. So I mean that this is a concrete also something. I mean that computationally the incorrect or not homogeneous field. But concrete also, this is also the heterogeneous material. It's okay or acceptable or something. So somehow we ignore or we skip that problem. So how do you think about this kind of program? Do you have any opinion about that?
It's related to Professor Kunieda's question. It's almost the same vein of thought. For example, if we're interested in fibers and the background mesh has this heterogeneity, it's difficult to investigate the effect of fibers by themselves. So having control of the background mesh allows us to tailor the simulation to the results, to the objectives of the analysis. So in some cases, it might be important if we discretize the aggregates, then we're down at a scale where we can assume each phase is homogeneous. But the standard model will present heterogeneity even at the fine scale.
Okay.
And I agree there is heterogeneity, but we want to control it.
Okay. Okay. May I ask?
Professor Nagai,
Yes,
I have
please.
a comment
Yes.
to the Professor Kunieza's questions. The second sentence, the society includes the journal, always requires correct and accurate result. So what is a correct and accurate result? I present that most persons test result, just only the one load different relationship is accurate one. Why? I cannot believe it. There is a big validation in the test result, and many persons required. Why your numerical result is different with the load displacement relations? Of course, if the same results, it's the numerical is probably the wrong, and so we have to discuss more what is the correct one, and for example, so I present several test results to check the internal crack pattern. Numerical size obtains many information, 3D information. So we have to try to get also the same information from the experimental side and compare it with both together.
Okay.
By continuing this process, I can what is the accurate and how to understand the correct. That is my comment.
Okay, thank you very much, Professor Nakamura. I totally agree with you, and I'm really impressed that your proposal, I mean that once we have such a discrete model that gives the cracking information, then that experiment can be changed thanks to the simulation. Simulation can show the detailed information. Then experiment or observation can be improved. Because of the advancement of the simulation. So that this is a kind of the history of the science. I mean that the modeling and the observation, always the one goes up, then the other goes up, the other goes up. So thanks to the observation, simulation also improved. And thanks to the modeling, the observation also improved. Something like that. So therefore that I'm really impressed with your presentation. And then most of the researchers somehow tend to be the only computational side or sometimes experimental side only. But you are doing both. Therefore, you have a new idea. That's really good things. So I want to go back to this kind of discussion later. But before that, I have a question to Professor Bolander again. So basic things. So that in the Professor Nakamura's presentation, that he made a truss model for the reinforcement, steel reinforcement. So then that is, I believe, this is a really the innovative advancement of the things in the RBSM. I mean, the steel reinforcement bar is modeled by the truss model. So this is what you did. Am I correct? Is it correct?
We didn't account for radial pressure. I think that Professor Nakamura has taken it several steps further.
Sorry, that point is not so clear. Only me?
I also the Professor Bolander's sound is not so clear.
Don't you have any? Can you try to talk again?
Yeah, can you hear me now?
Okay, no, it's okay. It's okay. I mean that maybe that 20 years ago or something you use together with Professor Saito or other colleagues, you introduced the truss model. Then that before that lattice model, like you inspired by the Professor Famiya or Schlangen, the Delft group, and also the Bajan or Xatis, the Northwestern group. They mainly use the lattice model or other models. But yeah, they did only the failure of the concrete material,
Right.
not reinforced concrete structures. But yeah, thanks to your proposal or your modeling, we can apply that discrete model to the concrete, to reinforced concrete structures. How could you get this kind of idea?
I think it was partly Saito Sensei's idea.
Okay.
So he was working here, he came as a student, and so I think lots of that he did. And what's nice when you try to do that in finite elements, with a finite element, you're making all these assumptions about continuity of the displacement field. And when you run a bar through the finite elements, it's not compatible. And so you have a very sophisticated approach. And then when you add the bar, it's a much coarser approach. And I think when you use lattice models, there's a better match. The modeling of the bar matches better to the modeling of the concrete. So I like the bar in what Professor Nakamura is doing is a good approach.
Is there any comments from Professor Nakamura?
For the river modeling?
Yes.
Yes, that is so the RBSM, the basic concept is the accumulation of the many springs. So the Professor Saito success to how to introduce the concept connect the springs. That is a very good idea and connect. So if the only use the springs by connecting the many materials, we can connect many materials and many structures and other phenomena. That is the basic concept that how to extend the RBS concept to considering the spring network. That is a very important concept, I think.
Right. Okay. Thank you very much. And then, let me go back to the slide for the panel discussion I prepared. So that, verification. I want to ask about the third one. That is micro scale, meso scale, macro scale, bridging the scales. Especially from the presentation by Professor Nakamura, we could see various application of the discrete analysis model. That includes the structural analysis and also the rather micro scale analysis, including the Professor Bolander's presentation. Then we often say that multi-scale. Multi-scale is a kind of the keyword maybe 10 or 20 years ago. But many people, and not only in the civil, but mechanical engineering or other in other fields, many researchers say that multi-scale, by integrating the phenomena from the micro scale, then we can go up the scale. How is the situation now for in this field, meaning the discrete analysis model? So do you have any, can you explain the situation or some further future perspective of the multi-scale concept using the rigid body spring model or discrete analysis model? Or Professor Bolander or Professor Nakamura.
So first idea of the RBSMs of the Professor Kawai is limited analysis. But then the Professor Bolander applied to the small particle, combination of the small particle. Then the RBSM change and move to the mesoscale analysis. And the concrete behavior, most concrete behavior is related to the micro cracking around the aggregate. And I said that my modeling scale of the element is usually I decide the 10 to 30 millimeter. This is the same size of the aggregate. So modeling by the cracking at the size this means that this can success to modeling the cracking near the aggregate. So the smoothly we start from the mesoscale analysis and can go up to the macro scale analysis. That is a merit and big first challenge of the RBSM. But the micro scale case is very difficult. I cannot discuss the detail. But the micro scale case is like Kunieda sensei's questions, mesoscale case, I can validate, but the micro scale case, it is difficult to validate and make a modeling.
Okay.
Sorry, no ideas for the micro scales.
Okay, so let's ask Professor Bolander.
We could do microscale or mesoscale analysis and then feed that into the spring properties. And it's the same in finite elements where you do a lower scale analysis and you use it for the integration points. And so I see a parallel there in both finite element technologies and then what we're doing with discrete models. I think both can benefit from multi-scale approaches. And for example, we have simulated cement hydration and used cement hydration to control the time variant properties of the springs. And so arguably that's transitioning scales because the cement hydration model is based on cement particle composition, cement particle size, water cement ratio. You're bringing all that information from a much lower scale into the spring properties. And then I think what Professor Kusadis is doing is another good illustration of a multi-scale model that in his approach, he's bringing in the aggregates explicitly and able to do structural scale analysis. And so I think that these discrete methods, there's many opportunities for multi-scale analysis.
Okay. Okay, so that yeah, we still have room to develop more. I mean that yeah, many researchers can try to connect the scales. So that is that yeah, really we have a future to do that. Yeah. Okay, sorry that so many several questions comes, but not so sure whether we can answer to that. But so yeah. Again, the Professor Nakamura, that yeah, just similar question, but that experiment you do to measure the cracking. So how can you V and V things? So when we can say that this simulation is good enough or really nicely simulated enough when you compare with that experiment. I mean that you show the cracking patterns in the experiment as well. So then how much can you compare with simulation now? For example, you show the beam test, shear failure, the cracking pattern using the DIC and so on. Then how accurately simulate now you can, or when you can say that it's enough good or something?
My impression is for the simulation of the fracture failure of the beam level and the shear failure of the beam level is enough to simulate. And in laboratory cases, first simulate, design the beams based on the RBSM numerical result. And first we simulate the result before test. And after the test, I compare with that. During the test, we compare with the numerical result. And if the test result is a difference with the numerical result, what is the reason we consider? Mainly the reason comes from the measurement method of the experimental site. So I believe, honestly, I don't know that many persons believe that our way is that I believe that numerical analysis in the general and the fracture and shear failure mode. And of course,
Okay, please.
and corrosion crack or the several crack. We observe the major crack problem is I think now the most cases to simulate successfully by basing the discrete element analysis model.
Okay. So in terms of the verification and validation, because your simulation can get more information than FEM. FEM can get somehow average response, but now you can get a detailed cracking pattern. Therefore, that verification also validation also become a little bit difficult. I mean that if you have an experimental result and find a very detailed cracking pattern, this crack doesn't match with simulation. Your simulation is not correct or something, even though the macroscopic low displacement curve is correct, but detailed cracking are different and so on. So do you think that V and V also getting difficult if we use the discrete analysis?
So, it depends on the purpose. Only the discussion is the load displacement relationship for apply to the design stage. Sometimes we require only the shear capacity or the fracture capacity. The case is that it is easy. So it depends on how to use the numerical result and how to validate. It is depend on our purpose and target.
And also maybe it relates to the comments from Professor Wu that in case of, for example, fiber, the location of the fiber is always different. I mean that when you do the experiment by experiment, was due to the boundary condition, the internal condition was they are always different. But we can somehow do the simulation of the fiber reinforced concrete by modeling all the fibers in it sometimes. So then how can we think about the difference between the simulation and the experiment? So Professor Bolander, you showed a nice presentation with a nice simulation result for the fibers. So how can you validate your simulation model with experiment? Do you have any comment or some idea how to confirm that?
When you have steel fibers, it's easy to use some sort of X-ray image or computed tomography. Steel fibers show up very nicely in X-ray images. And so we've done some comparisons when a slab was poured, and the pouring process induced bias on the fiber directions. So the people that produce these slabs, they cut out 3-point bend tests. And depending on where the beam was cut from the slab, the properties were quite different. So if you feed in the fiber positions, these discrete models do a good job. So a key point is knowing where the fibers are. If we know where the fibers are, the model can simulate.
So somehow discrete treatment and that average treatment, I mean, in the model. So maybe most of us are sometimes confused that some people say that if we make a finer mesh using the discrete analysis model, so that everything can be reproduced or can be simulated as it is. But we set some consider model at the interface between the rigid body and the rigid bodies. So that somehow this is a kind of average model between the small element. So then as Professor Nakamura also pointed out that at the micro scale, how can we verify or observe or measure the real phenomena? It's quite difficult. Then some gap always exists. So do you have any opinion about the difference or difficulty of this kind of thing, or that some people believe that if we make a very small mesh everything can be solved or something.
No. So I completely agree with what you're saying and Professor Nakamura's point that verification and validation should involve all relevant scales of the model. All relevant components of the model should be validated. And if we just validate based on global behavior, we don't really know whether the model is working or not.
Mhm.
And sometimes parameters are fitted. Most models have free parameters.
Mhm.
And some of these parameters are fitted so that the global response is correct or looks correct.
Mhm.
But the model might not be functioning properly, and we don't know. So I agree with what Professor Nakamura said in the presentation and in these comments that the V&V needs to be more rigorous and involve all the relevant components of the model.
Yeah. This discussion is not only for the discrete model, maybe nowadays, yeah, powerful computer we can use easily, so that we often see in the international journals that using the very fine mesh by FEM, then using the FEM very fine mesh, then some concrete failure simulation is done successfully or something. Sometimes using the very fine mesh shape of the aggregate also modeled as it is and so on. But it's not yet. How can we validate or verify these models? It's quite difficult. So that V and V or how measurement also become very important. Maybe.
We were looking at fatigue damage
Mm-hmm.
in macroporous concrete, and so after so many fatigue cycles, we stopped the test and then we impregnated the specimen with epoxy with fluorescent dye. And so we could see the microcracks at different stages of development under fatigue failure. And so that it would just take the experimental program becomes tedious. You have to stop the experiment at different stages and somehow interrogate or
Mm-hmm.
understand what's happening internally.
Yeah. Sometimes some researchers use some X-ray or something, then see the internal crack as well. So, okay, we come to the almost the time, but before going to the last question, that how do you think about the computational cost? I mean that now, for example, Professor Nakamura is doing a lot of simulations. That do you have any opinion that this is also maybe you get this kind of question that if you do such a large scale computation, how long is the simulation time and so on, including the future prospect? That how do you think about the simulation cost or computational time?
Computation time is a problem. For my case, is sometimes we continue to more than 1 week, 2 weeks.
Mm-hmm.
The very final mesh and very concrete is use a very final mesh and very strong nonlinearity. And the RBS case many point cracking and closing and opening to the cracking. That's a very difficult to converge situation. Of course, sometimes it's not local part doesn't converge, but globally it's converged. But the opening closing cases many points are working, so very difficult to so the computing time increasing this situation. But I'm a concrete engineer, so probably this problem will overcome the increasing the computational performance. I believe. I wait.
That's a correct way as a concrete engineer or civil engineer. Do you agree with that, Professor Bolander?
I agree, and we need to continue to attract junior researchers because they're usually better at the latest developments in computational technologies. So I have colleagues that are working with graphical processing units, GPU processing, and they're much faster. but I can't do that. I'm too old, to spend my time doing parallel algorithms, and we need cross pollination with people in computer science and just junior researchers that are excited about computation, because there's a lot of technologies that exist to help us. And so that's part of it. One, we wait for the computer to get faster, but two, we need to work with people that understand the current developments.
Okay. Yeah, that's also very important to attract young engineers or researchers, because nowadays civil engineering is not so popular, or concrete engineering also not so much, so that to attract the young engineers or researchers, yeah, we are doing the cutting edge things. We can fight against other fields as well by the computation and so on. That's also very important. All right, so yeah, I'm so sorry, but the time is very limited. So finally, I want to talk to you. I want to ask you ideas for the future prospect of discrete analysis model that you have already included in your presentation, but including all the discussion today and presentations, can you once again summarize some future prospect for the discrete analysis model? Firstly, Professor Nakamura, can you?
My idea, my hope is to find new mechanisms, because macro behavior of the concrete structure is originally, I believe, come from the meso levels and minor levels of cracking. So in only the experiment, it is difficult to image the micro cracking, the small cracking. So, but the discrete analysis model can give us the idea and image the very small levels phenomena, and from these observation in the numerical results, how do we get the new ideas, new phenomena, and how influence to the macro behavior? That is now I'm thinking to how to use this discrete analysis models.
Okay. Yeah, thank you very much. We are very happy that you as a concrete engineer doing the simulation and the experiment both, and then getting a new idea. That's really good things. Okay, so thank you very much. Professor Bolander, please.
I think that it depends where you are in the world or what country you're in. And in many places, we need funding. And I think the funding agencies currently is application driven. So what Professor Nakamura is doing is a successful approach, because we get money to do things if it's applied to some problem. And some of the work that I'm doing, the fundamental work, is difficult to fund. The basic properties of the spring network, the basic mechanisms of fracture, we have to put it into an application framework to get funding. And then once you have funding, then we can move the research forward. So I like what Professor Nakamura is doing, because it's application driven. And I think that's one key point, is we need to find applications that need computational support, and then argue for the discrete method.
Okay, thank you very much. So yeah, Professor Nakamura showed the many applications in the structure side, but Professor Bolander shows the application to the early age concrete properties. That is also very important, so keeping the good quality of the concrete structures. So yeah, we have more futures. And then I remember that 10 or 20 years ago, always FEM is the best, or FEM can solve everything or can do the design as well and so on. But in reality, reinforced concrete structure always having a cracking. Yeah, how to treat the cracking is the most important thing in our field. So that especially for the concrete engineering, that discrete analysis model is very suitable to solve the problem or to tackle on that, especially nowadays, maintenance of the structures, not the global behavior, overall behavior, but the crack width or crack depth and so on, detailed information become more important, and maybe we have a future in that field using the discrete analysis model, I think. Okay, yeah. I'm on, 5 minutes or past, so that I'm so sorry that many of you are giving the question from the Q&A box, but I'm so sorry we cannot read all the question, but I hope this discussion and the presentations by the two reading researchers is good information for you now and the futures as well. Okay, let us close today's seminar. Then before that, it doesn't work. Okay, yeah, let me introduce the next seminar, but we haven't yet decided the topics and the schedule, but we roughly think that we'll have the next seminar July or August. So yeah, we have your email address so that we want to keep in touch with you and then give information of the next seminar. Maybe it will be on the material side, not simulation, maybe the material experiment would be the topic for these frontiers of concrete technologies. All right, this is the end of the Frontiers of Concrete Technology organized by the JSCE, Japan Society for Civil Engineers. So thank you very much for joining today. Then once again, we really appreciate that Professor Bolander from the University of California, Davis, then Professor Hikaru Nakamura from the Nagoya University. Thank you very much for your nice presentations and nice discussions. We really appreciate it. Okay, so we are closing this seminar now. Thank you very much for joining today, all the participants, and then see you in the next seminar. Thank you very much. Thank you.
Goodbye, everyone.
Goodbye.